I'll now introduce the subtype relation. S is a subtype of T is read S is a subtype of T, or alternatively T is a supertype of S. So this less than operator basically represents is a subtype of less than into the colon in this notation. And so we read this as S is a subtype of T. Okay, so what does S being a subtype of T mean? Type S is a subtype of type T if any term of type S can be safely used in a context where a term of type T was expected. So notice that I'm saying that a term of type S can be used in a context where a term of type T was expected, and any term. And if this is true, if this statement is true, then we say that S is a subtype of T. Okay, so I'm going to show some examples to explain this. But the key words here are safely used and context. And they are not precise in this definition. And they are actually very programming language specific. And so when we look at examples, this will become clearer. So precise definition of S is a subtype of T is very programming language specific. And here are some examples of subtyping relations. So let's say my language has two types, int and bool. And let's say I decide that int is a subtype of int, which means if any term of type int can be used in a context where a term of type int was expected. Now this is pretty straightforward. In fact, as we're going to see later, every type is a subtype of itself. Similarly, bool is a subtype of itself. But notice that there is no subtyping relation across the two types. So neither is bool a subtype of int, and neither is int a subtype of bool. What does this mean? Well, let's say that we had an operation plus that was associated with int, which was the addition operator, and let's say we had an operator logical AND, which was associated with the bool type. Now, let's say the term true is of type bool. Similarly, a term false is of type bool. And because the logical AND operator is something that is acceptable on the type bool, so true and false is a valid expression. However, true plus false is not a valid expression because plus is not expected with bool types. Plus is only expected with int types, and true is of type bool. True is a term of type bool, and the type bool has nothing to do with the type int. There is no subtyping relation between bool and int. No, these relations basically don't say anything about what is the relation between bool and int. And so in this language, let's say true plus false is invalid, and similarly if I try to logical AND two integers, let's say 1 and 2, then that's also invalid. Now let's say, this is one example of a programming language. Now let's take another example of another programming language where they decide to have different relations between int and bool and the different subtyping relations. So once again, int is a subtype of itself, bool is a subtype of itself, but additionally the language says that bool is a subtype of int, which means that any term of type bool can be safely used in a context where int was expected. So for example, if I look at the operator plus, then 1 plus 2 is legal, but also because bool is a subtype of int, if I replace 1 with, let's say, true and say true plus 2, then in this language that would also be type correct. So true plus 3 is type correct. Similarly, true plus false is type correct because a term of bool can be safely used wherever a term of int, a term false of type true, bool can be safely used at any place where a term of type int was expected. Here a term of type int was expected because of the plus operator, and because bool is a subtype of int, I can use false here, all right? And it may have some meanings. For example, the plus operator may treat true as 1 and false as 0. It depends on the language. But notice that int is not a subtype of bool, which means that anywhere where bool is expected, it's not true that I can use an int. So for example, one logical AND with false is incorrect, because here this one is incorrect because I expected a term of type bool. Maybe I wanted to use a true here. Similarly, one logical AND with 2 is incorrect because we expected a bool, and but we are getting an int, and int is not a subtype of bool. It's the other way around. Bool is a subtype of int, but int is not a subtype of bool, and so 1 and 2 is wrong. But because bool is a subtype of int, true plus false is correct. Now let's take another example of another language. In this language, once again, int is a subtype of int, bool is a subtype of int, but let's say int is a subtype of bool. And in this case, these expressions here, 1 and false, 1 and 2 become correct, written in green, but true plus 3 and true plus false become incorrect, right? So subtyping relation is used to disambiguate the correct expressions, the type correct expressions, from the type incorrect expressions. And depending on how you choose the subtyping relation, you mandate what is correct and you specify what is correct and what is incorrect. So notice that subtyping is a form of type polymorphism. For example, in the previous examples, if bool was a subtype of int, then true can be used both as a bool with the logical AND operator, and true can be used as an int with the plus operator. In other words, a single term, true, seems to belong to more than one type because it can be either used as an int or used as a bool, and it will have a meaning depending on in which context it's been used. For example, if it's used with plus, then maybe it has the meaning 1, and when it's used with logical AND, then it has the meaning true. So subtyping is a form of type polymorphism. There are other forms of type polymorphism, and subtyping is one of them. In object-oriented languages, subtype is the same as derived type. So for example, if you define a new type using this keyword class, let's say in C++, then you have class A and you have some specification of class A. And then you can say class B is a derived type of class A. In other words, class B is a subtype of class A. So B is a subtype of A, and A is a supertype, or also called a base type in object-oriented languages, of B. Which basically means that a term of type B, in this example, this represents a term of type B, can be used safely where a term of type A was expected. So what is expected here was a term of type A because it's being assigned, or more precisely a term of type A star because it's being assigned to a variable of type A star. But because B is a subtype of A, it's safe to use a term of type B in a context where a term of type A was expected. Now notice that once again, what do I mean by safely used and what do I mean by context is very programming language dependent. For example, in C++, I can do this for pointers, but perhaps I cannot do this for, I cannot, for example, in C++ just do A equals B. All right. So subtyping relation is kind of has two keywords here, which is what do I mean by context and what do I mean by safely used, and the programming language will specify what it means. For example, here in C++, it means that it needs to be a pointer context, and it can be safely used in these ways, etc. So informally speaking, if S is a subtype of T, then a term small t of type S can be used in all operations of type T. Notice that small t is of type S, yet it can be used in all operations of type T because capital S is a subtype of capital T. But it may additionally be used in more operations specific to S because it is of type S, so it can be used in more operations which are specific to type S in addition to all operations that are acceptable for type T. So here are some properties of the subtype relation. A subtype relation is reflexive, must be reflexive. I mean, these are requirements of what a valid subtype relation in a language can be. It needs to be reflexive. Recall that in all the examples we saw, we said bool is a subtype of itself and int is a subtype of itself. And that just follows from definition. For all types S is a subtype of S, which basically means a term of type S can be safely used in a context where a term of type S was expected. Transitive. If S is a subtype of T and T is a subtype of U, that basically implies S is a subtype of U for all possible ST types ST and U. Once again, this follows from definition. If a term of type S can be used anywhere where a term of type T was expected, and the term of type T can be used anywhere where a term of type U was expected, then transitively a term of type S can be used anywhere where a term of type U was expected. And finally, a subtype relation is antisymmetric, which basically means that, well, if S is a subtype of T and T is a subtype of S, then they should essentially be the same type. So this is basically ensuring that you don't have two types that behave identically to each other. And if they do behave identically to each other, they're basically the same type. They're just different names for the same type. And so this is the antisymmetric property. If S is a subtype of T and T is a subtype of S, then S must be equal to T for all types S and T. In fact, because of these properties, you can specify the subtyping relation through a drawing as a tree. So for example, if these were your subtyping relations, this is the corresponding tree. Every node in the tree represents a type and the arrow represents the subtyping relation. So for example, the arrow here has this shape, and so this basically means that bool is a subtype of int. Notice that the arrow has the same orientation or direction as the subtyping relation operator in this statement. And notice that reflexivity just comes for free in this diagram representation because every node is a subtype of itself. Transitivity can be basically seen. So for example, if some other type T was a subtype of, if bool was a subtype of T, then by transitivity, int would also be a subtype of T. Now I want to emphasize that subtyping and typecasting are two different things. So for example, these are examples of valid syntax in C and C++. So you could say int I equals character C. Now it may appear that because character C is a term of type char in C, so maybe, and because it's appearing on the right hand side here, it may appear that character is a subtype of int. But in fact, in C and C++, character is not a subtype of int. Similarly, you can write code like this. You can write float f equals 3, and it may kind of, make it appear that int, because 3 is an integer, int is a subtype of float, but int is not a subtype of float. Okay, neither is float a subtype of int, and so on. Then how come these are valid syntaxes in C and C++? If char is not a subtype of int in C, float is not a subtype of int in C, then why are these valid syntaxes? Well, it turns out that C and C++ also support what is called implicit or explicit type conversion, also called typecasting. And so subtyping and typecasting are two different things. So when you write code like this, where you say int I equals character C, the compiler implicitly inserts a type conversion operator here, int, and you could have done that yourself too. And this is something that the compiler provides to the programmer as a matter of convenience. Different compilers may choose to do different things here. For example, some compilers may say, I'm not going to do implicit type conversion. These implicit type conversions are implemented by compilers for convenience, and they should not be mistaken for the subtyping relation. Because the subtyping relation is actually a much deeper requirement, which pertains to language design itself, whereas this implicit type conversion is just a matter of convenience for the programmer. All right. Notice that subtyping relation is designed by the language designer. Depending on what the designer wants from his or her language, they will design the subtyping relation accordingly. And this is a very, this is an art, and various considerations need to be taken when you are designing a language. One of the considerations that I show here, which is kind of subtle, is function polymorphism or overloading. For example, languages like C and C++ allow simultaneous declarations of the same function identifier foo, but which take different types of arguments. For example, one of the arguments could be int comma int. Another signature could take, the first argument is character and the second argument is integer. And the third could say, oh, the first argument is integer and the second argument is character. Now notice that if character was a subtype of int, if char was a subtype of int, then disambiguation becomes much harder. For example, if the user types foo with two characters, let's say character A and character B, now it's, if character was a subtype of int, it becomes much harder to say which one of these should be called. Should the first one be called, should the second one be called, or should the third one be called? Because, well, I mean, this is, if character was a subtype of int, then it appears that either of them can pattern match, right? Because character is being used in a context where character is expected, and a character is being used in a context where int is expected. And because character is a subtype of integer, it may appear that the second function can get called. But the same logic also applies for the first and the third functions as well. So when the language designer is making these choices of the subtyping relation, there are all these considerations they have to consider.